Okay guys, I just made this quick video because I want to see if we're all on the same page and I'm trying to understand this problem. So just take a look at this video and basically point out where I'm wrong and what I need to fix, and so we can get on the same page for what we need to do. So the question is, how do we stop a spinning rocket going Mach 1.5 up at 10,000 feet? That's our ultimate goal just for this rotation problem. Right, no problem. Alright, so the first thing is we're definitely looking at the pressure procedure for dumping gas through nozzles. So we're going to have a tank and there's going to be some gas, probably most likely carbon dioxide, and we're going to have it regged out. We're going to assume around a 4,500 psi tank, and we're looking at right now, just for guesstimates, 100 psi output. And some of the things I was coming across was we need to calculate our mass flow rate, so later we can calculate the force that this vectoring provides. And the mass flow rate is going to be pretty difficult to actually get, and we can do some estimates. There's this Pasolini equation, but it's going to be kind of difficult to figure that out. I think we can do experimental stuff. It might be better. And then we can kind of spitball it once we get it on the table, get the system up and running. So here we are looking at the tank, and there's going to be some kind of reg. It's going to go through some kind of splitter maybe. We're looking at different things here, but assuming that we have a split option with a solenoid that's going to be able to open and close and dump gas in each one of the different systems of nozzles. And in this case we're talking about rotational nozzles only. So yeah, if we can get the mass flow rate, I believe this equation is correct, force equals the mass flow rate times the velocity. And if you look at the units, it's mass flow rate is kilograms per second and velocity is meters per second, and that gives us newtons. So if we can get that mass flow rate coming out of the nozzle from the 100 psi regged, then we can figure out that force coming out of the nozzle. So that's like one of our first things we need to kind of figure out. Alright, so now let's go ahead and look at the rocket itself. It's not just a nozzle spinning or spitting out air on the ground. So there's the dynamics of the rocket itself. We have to consider the mass distribution, the radius of the rocket, and the of course the angular velocity of the rocket in the air, and then any environmental factors. So here we've got our IMU. I don't know if this is how it's going to look, but we got a nose, parachute, eBay, second stage, IMU, first stage. In the IMU we'll have the 6 different possible controls with clockwise and counterclockwise rotation with the pitch and yaw, but we're just looking at the rotational stuff today. So let's see here. Okay, yeah, so there's a center of mass and center of pressure. There's going to be some kind of angular velocity on the rocket, and we're going to have to provide a counter roll to stop that angular velocity. We can look at angular velocity. I actually wrote this wrong. Omega should be, the little omega should be angular frequency. Big omega is angular velocity. But there's also to consider the tangent angle of the nozzle, because I don't think we get directly 90 degrees off the rocket, and then those other things we're going to look at. Alright, so here's the nose. There's like a vector kind of looking, the dot, so it's like pointing out towards the screen. There's going to be some kind of angular frequency, and we have to provide a counter roll, and that's why I just put this gamma angle in there, because say we get the nozzles at, I don't know, 60 degrees to tangent, then we'll have to do this quick. Our force would be, you know, the mass flow rate times velocity, and then times sine gamma. Gamma will give us the force tangential to the rocket. And then just some quick, real quick rough, I don't even know if this is right, guys, you're gonna have to tell me, but you know, there you have it, a cycle, some frequencies, some omegas. Yeah. In this example I would need 16 pi squared newtons to counter, and that was assuming the mass was 1 and the radius was 1, and which is all kind of ridiculous, but you know, that's an idea. That's, I'm guessing, how we're getting there. Alright, so whatever, we figure out the force to counter roll or angular frequency, but how is the best way we can apply a force to counter? And the idea was, Brian was thinking about this, I think Evan, you thought of this too, was doing a burst. And the idea is basically we'd set up a number of bursts for a range of angular frequency that we're reading, and we would calculate beforehand what one burst was worth. I just made an example here, 1 Newton. So like if we bursted it for like a half a second, we would figure out the time it would take with the PSI and the mass flow rate to get what kind of force we're looking for. So I don't know, if we had 10 bursts, say we had 10 newtons of tangential force for this particular frequency range. These are all just example numbers, but obviously we decrease the number of bursts the lower the angular frequency, and that way we could have time for the sensor to read after the burst and see what it's at. So we're not just dumping the whole time, but we send a burst, we correct a little bit, we read, and then we reapply another burst as needed. So that's just the idea there. Alright, so then finally, if we can get this whole system up and running, we're going to just basically put it on a spin table, and then I think experimentally we can kind of figure a lot of this stuff out. But it would be nice to have some kind of a theory behind it so we know if we're in the right direction. Plus, I mean, going from the table to the air, it is going to be a little different, so we're going to need to know how to adjust. So experimental won't get us there by itself. Alright guys, let me know what you think. Thanks for watching.